Okay, can we start now? Write down the chapter we are going to start today is amines. Okay, I'm getting married next month. Thank you. You didn't know this? Yes, at that time he told you, no, but that time it was not at all fixed. Now it is done. 12th of December. Thank you. Thank you. Thank you. You will also get married. You want? Ramcharan? What? You don't want? Okay. Anyways. See, this is ammonia, right? NH3 is ammonia. Right. And when I replace one of this hydrogen atom by any alkyl group like this RNH2, right? Then this we call it as amines or 1-degree amines. Right. If you remove 2 hydrogen by alkyl group, it becomes R2NH. This is 2-degree amines. And when you replace all the hydrogen by alkyl group R3N, it becomes tertiary amine or 3-degree amine. Okay, so these are the derivatives of amine. Derivative of amine. Okay, so this is the one thing I think you have to keep in mind. One more thing here, the most of the reaction of amine, if you see, this nitrogen and hydrogen bond takes part in the reaction. Means this hydrogen actually takes part in the reaction, and it goes on, stepwise reaction actually we have over here. All these hydrogens, because of the electronegativity difference, has tendency to react in the reaction. Understood? Fine. So we'll see those reactions one by one. Okay, preparation and reactions. First point in this you write down, due to presence of lone pair, amines are basic in nature. And this particular relation is important. This particular relation is important. Okay. So, and there are two different order we have for this. Okay. And that is the basicity order you write down in gaseous phase. Basicity order in gaseous phase. Okay. These two you must remember. It is very important. In gaseous phase, the basicity order is found to be this tertiary amine, 3-degree amine is most basic, then secondary, and then primary in gaseous phase. Why it is very clear from this particular example you see. Tertiary amine is this, right? Tertiary amine is this with one lone pair on the nitrogen atom, and tendency to lose lone pair is nothing but what? Basic nature. Correct? So when all these alkyl group has tendency of plus I effect, right? So the electron density on nitrogen increases as the number of alkyl group increases, and hence the tendency to donate lone pair of electron is maximum. Correct? And that's why the basicity order is found to be this. Yes? Now, in aqueous, these two order is very important, okay? In aqueous phase, the order is found to be this. 2-degree amine is most basic. Then we have 1-degree amine, and then we have 3-degree amine. Okay. Now in this you write down the reason. This is only true. This is only true why it is important you see. If the alkyl group, if the alkyl group is methyl CH3. Okay. In case of ethyl, next write on next line. In case of ethyl, the basicity is found to be 2-degree maximum. Then we have 3-degree, and then we have 1-degree. I'll tell you. Okay. So in this example also you write down alkyl group means what? CS3 whole twice NH, and then we have CS3 NH2, and then we have CS3 whole thrice N. This is the order in case of methyl. In case of ethyl, the order is C2H5 whole twice NH, C2H5 NH2, and then we have C2H5 whole thrice N. Sorry, it is whole thrice, not 231. NH2. This is the order we have. Now, the reason of this you write down. Write down in aqueous solution. See, in gaseous phase, what happens? The basicity depends only on the plus I effect of these groups, right? But in aqueous phase, along with this plus R effect, we have two more effects that takes part into this process, and that is hydration effect and static effect. Okay, write down this thing that in aqueous medium, the basic strength of amines, the basic strength of amines depends not only upon depends not only upon the electron releasing effect, but also not only on the electron releasing effect, but also on steric effect and hydration effect. Steric effect and hydration effect. What is steric and hydration effect you see? See, first of all, if you have this compound that is CH3 and H and H, and then we have CH3 and H CH3, and the last one we have CH3 and CH3 and CH3. Now in this, when you put these molecules into water, that is in aqueous medium. So in aqueous medium, what happens? All these hydrogen has tendency to form hydrogen bonding off with oxygen like this. And this hydrogen bonding provides what? Stability. Yes or no? These nitrogen has lone pair, one lone pair. In this case, since there is no hydrogen attached to nitrogen, So there is no hydrogen bonding here, no H bonding, right? Along with this, at the same time, this CH3 also increases the plus I nature or electron density on this nitrogen atom, right? So when you only see the I effect, which is plus I effect over here, according to that, the basicity of this should be maximum, then this, and then this, right? Right. But when you see the stability factor, this is the hydration effect, hydrogen bonding that takes place. Because of hydrogen bonding, this one is more stable, right? And this one is least stable, right? So according to this, if you see, if this is more stable, the tendency to donate electron pair will be more here, right? Will be less here, correct? Again, what happens, you see, in case of when you have ethyl group present over here, then around this nitrogen, the most of the space are occupied by the ethyl group, right? If you have bulky group present over here, so most of the space are occupied by the alkyl group present over here, and hence there is no space over here, so that this electron pair, this nitrogen can donate and forms and show the basic nature. If all the space around the nitrogen atom is covered by this alkyl group, which is possible when the alkyl group is bulky, then tendency to lose lone pair is less and hence the basicity decreases. Right? The first point, see, these two are contradictory point. Because of plus I nature, the electron density is increasing here and hence the tendency to donate lone pair should be more. Correct? So if you see only plus I nature of this, the basicity should increase. But at the same time, when the plus I nature is increasing or alkyl group is increasing, at the same time, what happens? The space around the nitrogen that is occupied by these alkyl groups, and then we don't have many space or more space here, so that this lone pair can be donated, right? So since, and that is the steric effect we have, steric hindrance or steric effect. So because of this steric effect, the tendency to lose this lone pair of electron is less and hence the basicity decreases, right? So these two logic that I told you, these two are contradictory to each other. So the net effect of this molecule is the resultant of these two effects, right? In between these two effects. So that is what it is found to be. When CS3 is there as alkyl group, then the order is found to be maximum for 2, then 1, and then 3. But when C2H5 is there, ethyl group, suppose we have ethyl group here, here, and here. So obviously larger alkyl group, larger plus I nature. More will be the electron density here. More should be the basicity of this compound. But again, what happens when you have larger alkyl group? Large will be the repulsion also, steric hindrance also. More space around nitrogen atom will be occupied by the larger alkyl group. That will decrease the electron releasing tendency even more, right? So that is why the net effect of these two, the effect of these two effect, that is plus I and steric effect, is found to be 2, 3, and 1, 2 degree, then 3 degree, and then 1 degree for any alkyl group like C2H5 in aqueous medium. But for CS3 like species or like molecule, when we have CS3, it is 2, 1, and 3 degree for CS3. So net effect is found to be this, right? This is the explanation. Understood? Okay. So these three effects you have to keep in mind. Okay, you have to write down all these things. Okay. So that the same thing you write down. In case of larger alkyl group, in case of larger larger alkyl group, in bracket you write down bigger than CH3. Larger alkyl group, bracket write down bigger than CH3. For example, ethyl, propyl, etc. There will be steric hindrance there will be steric hindrance, and hence the stability due to plus I effect. Stability due to plus I effect predominates over the stability due to hydrogen bonding. Hence, 3-degree amines are more basic than 1-degree amines. Understood? So whenever like this, if you have two different effects contradicting to each other, so we cannot say by looking at the molecule, okay, this should be the order or this should be the order. In that case, whenever more than one effect taking place in one particular molecule, then all those, the net order that we write in these cases, all those order becomes experimentally in that case. Experimentally, we determine the order and then we try to explain it. Okay. So in both the cases, secondary amine is most basic. 3 and 1 we have in case of C2H5. When we have ethyl E, 231 order you have to follow, 231. And when we have methyl M, it is 230. 2, 1 and 3. This you have to memorize, it is important. Okay. Now you see the next one more point to write down. As percentage S character increases, basicity decreases. Why basicity decreases? Why basicity decreases? Because as percentage S character increases, electronegativity increases. And when electronegativity increases, tendency to lose electron, decreases. And that is why the basicity decreases. Is it clear? Tell me the basicity order of this. CS3 and S2, lone pair. CS3 and double bond CH. CS3, CS3, C triple bond N. What is the basicity order in this? 1, 2, and 3. This is what? This is sp hybridized. This is sp, and this is sp3. Percentage S character is maximum in sp hybridized 50%, right? So basicity of third one is minimum, then second, and then one, right? So these two factor you must keep in mind. Now you see the various reactions. You copied on. I'm just coming in a minute. Okay, just a minute. Okay, so see, like there are various intermediates we have. Okay, and like we know, cation, carbanion, all these, right? Similarly, there are one more. Carbenes is also one of the intermediate we have. Similarly, there is one more intermediate, and that we call it as nitrines. You must have remembered this. I told you this in aldehyde ketone chapter that we'll discuss nitrines in amines chapter, right? So there are various reactions of this chapter that takes place by the formation of nitrines. It is an intermediate, right? So in all, like what all the cases we have where the formation of nitrines takes place, that first of all we have to understand. So what is nitrines? Nitrines is the nitrogen atom which has two lone pair on it and one vacant p orbital. This is vacant p orbital. Okay, I'm not drawing that p orbital because every time we have to write down this. I'm just using a box to represent the vacant p orbital, right? So this box is the vacant p orbital, correct? Few points about this nitrines you write down. It is, you obviously you see 2 plus 2 4 electron we have, so it is electron deficient. Electron deficient. Next, what we can write, it is neutral. There is no charge on it. It is neutral. Third one is monovalent. Actually, we have one bond also here. It is attached with carbon. So that's why it is monovalent. Third one, total number of electron is 6. Total 6 electron. How it is 6, 2 plus 2, 4. And then 2 electrons will be here in this bond, right? So 2 plus 2 plus 4 plus 2, 6. 6 electron, electron deficient. Okay. And obviously, when 6 electron we have here, so octet is incomplete. Correct? One more point you write down here, can never be the product in any reaction since it is an intermediate. Can never be the product in any reaction since it is an intermediate. And we know already this thing that any intermediates can never present in the product, right? It forms during the reaction. Intermediates are forms during the reaction and destroys in during that reaction only, right? Finally, we'll get the product. Formation of nitrines you see, which is possible in various cases, and then write down whenever we have this kind of molecule, right? Write down R N double bond N double bond N. Okay, where here we have the positive charge, right? And here we have the negative charge. It is azide kind of compound. Okay, alkyl azide, NaN3. NaN3 is what? It is a sodium azide, right? So this is alkyl kind of compound. Whenever this kind of compound we have, in three cases, nitrines formations are possible. And those three cases are what? When you when you heat this compound, right? When you strike with light onto this compound, or when you are using very high temperature. Very high temperature. In all these three cases, formation of nitrines possible. Okay. How this nitrine formation takes place? You see, in this nitrogen also has two lone pair on it, one negative charge, right? So what happens? This lone pair comes over here in this bond, right? And this pi bond comes onto this nitrogen atom. So what happens here? This forms Rn with lone pair on it. One lone pair was already present over here. This lone pair as it is, this bond pair goes here. This becomes the lone pair. Then N, the positive charge will be as it is, triple bond N, right? Triple bond N, like this we have, and one lone pair onto this. This nitrogen, since it takes this bond pair of electrons, so this will have the negative charge on it. Now, finally, what happens? This from this particular intermediate, this nitrogen is electron deficient now. It takes this bond pair of electron and goes out as N2. So N2 comes out plus, see here, this will have one electron here, one electron here. When both this electron pair is taken up by this nitrogen, so obviously the orbital in which these electrons are present becomes vacant now. That orbital is the vacant p orbital, and we'll show this vacant p orbital like this. Okay, this is how the nitrene formation takes place. So here the nitranes will be R lone pair, vacant p orbital plus N2. Understood? Write down the various product into this. When you heat this, pH S double bond O, N double bond N, double bond N, positive and negative, and you are hitting this. One more you write down, CS3, C double bond O, N double bond N, double bond N, negative, positive. Okay, what is the product we get here? H, N, two lone pair, and this plus N2. Yes, here what we get? pH S double bond O, N plus N2. And here we get what? CS3 C double bond O, N plus N2. N2, right? Okay. But this thing here, it is again not stable. Okay. So here after this, you write down here. Only this one you write down in this product. Write down here. Now, if nitrene forms adjacent to carbonyl group, if nitrene forms adjacent to carbonyl group, then it is not stable. Then it is not stable, and Wolff rearrangement takes place. Wolff rearrangement takes place and it gets stabilized. Now, what is Wolff rearrangement? CS3, C double bond O, N lone pair on it, and one vacant orbital. Wolff rearrangement means what? This CS3, this CS3, take this bond pair from here, and this will migrate onto this nitrogen atom. Okay, because this nitrogen has one vacant p orbital, it can accommodate these two electrons easily over here. And when it migrates over here, This electron pair comes over here, and this pi electron goes onto this oxygen. Sorry, this is not. This will not go because already this bond has been no broken. No, this bond has been broken. This lone pair only comes over here. So what we get here, you see, this CS3 combines with this nitrogen, we'll get CS3N. Lone pair comes into the bond pair, so double bond C, double bond O. This we call it as, with one lone pair on the nitrogen atom left, we call it as isocyanate. Isocyanate, correct? So this kind of rearrangement, the migration of this alkyl group to this nitrogen, to this nitrogen, takes place only when we have carbonyl group present into this. When the nitrene formation takes place adjacent to this carbonyl group, then only this Wolff rearrangement takes place. Is it clear? Okay. So this is the one possibility, is one type of compound, which is the azide type compound we have, in which the formation of nitrene is possible. Another possibility is this. Second possibility, if this nitrogen attached with one alkyl group, one hydrogen, and other living group we have here, L, any living group. Now when this reacts with any base, in presence of any base, right, this is negative sign here, right, this is negative sign, presence of any base, this base takes this H plus from here, right, and this pi electron, this base takes this H plus from here, this pi electron comes over here, and this L comes out as living group. This is the living group we have, like chlorine, bromine, anything. Okay, so when you heat this in presence of a base here, then this forms Rn. One lone pair was present already, and when this leaving group comes out, it creates a vacant p orbital here. DH will be as it is. Leaving group takes the lone pair and has one negative charge on it. This is how the formation of nitrines takes place in this kind of compound in presence of base. Right? Now, what all possible bases are? We can have OH minus, right? We can have RO minus, we can have NH2 minus, or THO minus. All these bases are possible into this. Understood? Few examples you see. That is, suppose CS3 NHCl. Base, suppose I am taking OH minus, write down the product. CS3 C double bond O NHCl in presence of base. Write down the product in this. Hmm. Yeah, so there will be Wolff rearrangement in this, right? So here the product will be what? CS3N lone pair, one vacant p orbital, H2O plus, Cl minus, and here it will be the first will get this CS3 C double bond O, and with two lone pair, one vacant p orbital plus H2O plus Cl minus. And in this what happens? Wolff rearrangement takes place. This will migrate over here and will get CS3 double bond sorry, single bond N, double bond C, double bond O, isocyanate. Right? Now you see there are few reactions which involve the formation of nitrene and the reaction proceeds, right? So first write down the reactions which involves the formation of nitrene, which involves nitrene's formation. Reaction which involves nitrene formation. Which involves nitrene formation. Okay. The first reaction you write down, that is Hoffman Hoffman bromamide reaction. Hoffman bromamide reaction. This reaction we have done. Curtius reaction, Schmidt reaction, MIDT, Schmidt reaction. And the fourth one is Beckmann rearrangement. Beckmann rearrangement we also have done in aldehyde ketone. All these reactions follows formation of nitrines and the reaction proceeds. Right? Done? Okay. Our first reaction you write down, that is Hoffman bromamide. Bromamide reaction. The reaction is what? When amide RC double bond O NH2. When amide reacts with bromine in presence of any base, can be KOH, it can be NaOH, right? And when we heat this, what we'll get? We'll get RNH2, right? That is 1 degree amine. We are getting 1 degree amine from this. Okay, this is the preparation method of amines also. So now we are going towards the preparation method of amines. Okay, 1 degree amine we are getting. Okay, and this amine has one carbon less. You see RCONH2 and gives you RNH2, right? So now you see the mechanism of this. Okay, like one or two reactions, I'll show you the mechanism, but all these mechanism are not important. This question was asked in the test, right? Kondania, you asked me this. NH2 and D2 was there, right? RC double bond O NH2. Now when this, sorry, NH2, when this reacts with this OH minus from the base, what this OH minus do? It takes this H plus from this, right? This H plus takes this OH minus. So you'll get R C double bond O N with two lone pair here and H plus H2O. Okay. Now this lone pair will react with this Br2 molecule. This lone pair comes over here, and this bromine will take this lone bond pair and goes out. So this forms RC double bond O N H Br and one lone pair on it. And one lone pair on it. Again, we'll have a negative charge also here. Okay, so we'll get this. Now from this, what you can do when you have a base again OH minus, what happens then? From this, can you tell me? Yeah, what we'll get here? So this is the N hydrogen and one leaving group, right? So similarly, it forms what? R C double bond O N and one vacant p orbital plus H2O plus Br minus, right? Now in this, what happens? Wolff rearrangement. So it gives you R N double bond C double bond O. This is what we get. Understood? Now in this, this is the first step reaction where we get this nitrene forms and we get this isocyanate. Now in this isocyanate, the last step reaction is what? Rn double bond C double bond O with the base OH minus, and this base will attack onto this carbon. Okay, and this pi electron goes here onto this nitrogen. So we'll get this Rn C OH double bond O, and on this nitrogen we have two lone pair on it. Correct. Now in this, what happens? There is proton exchange takes place. Okay, so this pi electron actually goes here, and this H plus comes out from here, minus H plus, and this H plus will attach onto this nitrogen atom. What you get? Rn H C double bond O and O minus. This we call it as proton exchange. Okay. Another, if you draw this structure, draw the another form of this. This O minus comes over here. This nitrogen will take this bond pair and comes out as R and H with two lone pair on it plus CO2 goes out. Now, in the last step, H plus from the solvent, H plus from the solvent or this base that you are using here, KOH, NaOH from there. This H plus will attack onto this lone pair of nitrogen, and finally you get R NH2, right? Plus CO2 plus OH minus. Okay, so this H plus you write down here, it is coming from the solvent, which is the base over here, which is coming from the solvent. Understood this? This Wolff rearrangement is the rate determining step, right? This has been asked in JE. Okay, this step is RDS, asked in JE. Remember, this is important. Okay, just I'll give you a few examples on this. Okay, then we'll start the next reaction after the break. Okay. Just see how do you write down the product? You have started from this, right? Amide. And final is what? This R and NH2 joins. R NH2 will get this as answer. This is again 1 degree amine we have. So this reaction is helpful to get 1 degree amine. Okay. And one thing you must keep in mind, and that was the question in the test, this hydrogen that you get here, it is coming from the solvent, because you see here this hydrogen, one thing you see, this Br comes over here, hydrogen goes out from H2, right? Here you see this hydrogen attached over here. This H2 is coming from the solvent. If you take NaOD here, your answer will be RND2. KOH here, RND2, like that. So that you must write down in your own words. Okay. So this KOH will give NH2. Correct? Only thing is what? RNH2 you have to join. And this hydrogen must be coming from this hydrogen. If it is D, then here also we'll write down D. Few examples you see. Tell me the product in all these quickly. Ethyl C double bond O NH2, and we are using Br2 NaOH, Br2 NaOH, and we are heating this mixture. pH C double bond O NH2, Br2 KOD D2O, H2O also you write down here. RC double bond O NH2 NaOBr or KOBr. Tell me the product. Yeah, since we have hydrogen here, so here the product will be EtNH2. Here we get what? pH ND2. Sorry, ND2. Here we get what? You also get RNH2. See, this if you write, or if you write Br2 NaOH, both are same thing. Right? Actually, you see this reaction goes like this. When you take this NaOH plus Br2, so this OH minus combines with Br2 as HOBr, and Br minus goes out. Right. Now this HOBr with this OH minus from the base, this hydrogen H plus will take out. So it forms H2O and OBr minus. This OBr minus and Na plus will join, and it forms NaOBr. So when you write NaOBr or you write Br2 plus NaOH, both are same thing. There is no difference into it. Both are Hoffman bromide only. Understood? Yes. So all these reaction you see, we are getting 1 degree amine, 1 degree amine, 1 degree amine everywhere. Okay. What is the product here in this one? We'll get the last one. CS3 C double bond O NHCS3 with Br2 OH minus, and we are heating this. What is the product here we get? CS3 NH2. CS3 CS3 NH2, right? CS3 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 whole to NH. That is what we get. Huh? This CS3 and this group will join, no? Huh? This is not a living group. This is not a living group. That's why this reaction does not takes place. Understood? This nitrene does not form into this. And anyways, if you have this CS3, so if you write down, you'll probably write down 2-degree amines. But all these reactions you see, we are getting 1-degree amine. Hoffman bromide only gives you 1-degree amine. It never gives you 2-degree amine. So for Hoffman bromide reaction, this nitrogen must contains only hydrogen. We should not have any alkyl group present over here. Understood my point? It's fine because Cl may come out, but we should not have any alkyl group attached with this nitrogen because these methyls, ethyls, any alkyl groups are not a good living group. Understood? Okay, so we'll start the class after 10-15 minutes. Okay, take a break. Okay, you there? Yeah. See, one question that has been asked on this in JE exam that I'll give you now. The last one for this, then we'll move on to the other reaction. And the question is this: we have a benzene ring, and with this, it is attached with CND2 and double bond O this side. Plus, we have the another compounds. Here we have CH3 and CNH2 double bond. This when reacts with Br2 and NaOH, and we hit the product in this. Okay, so the product we get into this, see, this and this will independently reacts with this Br2 and NaOH. So you just first of all you see, assume this reactant is not given. How this will react with this? The product will be what? A ring, benzene ring, and then here what we have? NH2. When this reacts with this, correct? Plus, now this will react. So this has nothing to do with this reaction. Okay. So the another product will be, here we have CS3, and then it is NH2. This is the answer. This question was asked in JE exam. Ramcharan, you there? Okay. Okay. Next, write down the next reaction, that is courteous reaction. In this reaction, you see acyl chloride RC double bond OCl is heated in presence of sodium azide H2. Product that we get here is RNH2, which is nothing but 1 degree amine. Okay, whatever alkyl group we have, with that only the product forms. Okay, how this reaction goes, you see, NaN3. Obviously, this Na will take this leaving group, NaCl forms, and this N3 attached with this C double bond O. In NaN3, the structure is this: NaN plus and minus. Okay. So now here what happens? NCl goes out and it forms R C double bond O. Yes. Can you tell me next what happens when you heat this? So obviously this lone pair comes over here. So we'll get R C double bond O N with vacant p orbital. Correct? Plus N2. After this, what happens? Wolff rearrangement. So that forms R N double bond C double bond O isocyanate. Now again, this isocyanates reacts with OH minus from this H2O. This OH minus will attack onto this carbon, and this pi electron goes onto the nitrogen. It forms Rn, right? Negative charge on it, COH and double bond O. Okay. Next, what happens? But this H plus and H2O. This comes over on this nitrogen atom. It forms RNHCOH. Then again, what happens? This H will give this bond pair of electron here, and this bond breaks, CO2 goes out, and RNH2 forms. See, I'll write down here only, you see. When this H plus comes over here, you'll get this RNH COH and double bond O with one lone pair here. Now, when this bond pair comes over here, right, this bond pair on this nitrogen and this H plus will attack onto this nitrogen. So we'll get finally what? RNH2 plus CO2. CO2, sorry. CO2. Right? This is for this acyl chloride for this reaction takes place. Right? We use NaN3 and H2. For ester also, this reaction takes. See, here also, we are getting 1 degree amine. So Curtius reaction also gives you 1 degree amine. This you must remember. Okay. The same reaction you see with the help of ester. With ester, how this reaction proceeds. So with ester, RC double bond O, OR dash. Now for ester, we required three different reagents. First is hydrazine, NH2, NH2. Then we are using HNO3. HNO3, we also write it as NaNO2 plus HCl. HNO2, sorry, not NaNO2. Third one is H2O. So in this, when the reaction proceeds, first of all, the product that you get here is R NH2, 1 degree amine, plus R dash OH plus CO2. Okay. RNH2, you see the alkyl group which amines forms is the alkyl group which is attached to the carbonyl group, not with oxygen. Take care of this thing. Fine? Yes or no? So you see how this reaction goes. See, this reaction we use, first of all, when you use NH2, NH and H, this one of this hydrogen takes this R dash O and forms, see what happens, this lone pair of this oxygen will take this H plus from here, and finally R dash OH goes out. Okay. And the product that you get here in this is RC double bond O, NH, NH2. Correct? Plus what we get? We get R dash OH. Yes. Now in this, when you use HNO2 here, then we get our HNO2 here. Okay, so R C double bond O, NH, N, triple bond N with positive charge. Okay. In this, when you heat this, so obviously this N2O goes out and it forms RC double bond O, N, NH, right? RC, just a second. When it goes out, so we'll have that. So we'll have one lone pair, one H, and the vacant P orbital. In this again, what happens? H2O that you have from that H2O, it takes H plus, forms H3O plus, and we'll get here the lone pair again. So that will be uh, R C double bond O N with two lone pair and one vacant p orbital. Then isocyanate forms Rn double bond C double bond O. And from this, again the reaction is same. OH minus attack onto this carbon. This bond goes here. Then H plus comes onto this nitrogen, and all these things are same over here. Okay. So like this you get with H plus H2O. We'll get R and H2. Again 1 degree amine. Done. Next to write down Schmidt reaction. Sorry. Schmidt reaction. Write down in this reaction carboxylic acid in this reaction carboxylic acid reacts with N3H hydrazoic acid. It's probably hydrazoic acid or N3H reacts with N3H followed by followed by the hydrolysis in acidic or basic medium. Any medium we can take. So the reaction you see RC double bond O OH reacts with N3H. Then we have H2O with H plus or OH minus. Anyone. So in this again we get RNH2 plus H2O and CO2 goes out into this. Again you are getting 1 degree amine into it. All these reactions you see we are getting 1 degree amine. The mechanism I am not writing down. Okay, you can do this easily. Okay. This H2O first of all OH minus OH take this H forms H2O out and this N3 attached with this. And then N2 comes out from that. Wolff rearrangement takes place, we forms isocyanate, and then the reaction goes like those reactions we have already done. Okay? Understood? Ischemic reaction we have done in case of aldehyde and ketone, right? We have done it, aldehyde and ketone. Okay, so that will not do again. In this, just one point you write down note. In ischemic reaction, carboxylic acid, the reaction that we saw just now, gives 1 degree amine. If you have aldehyde, it gives cyanide or secondary amide. Okay. If you have ketone, then it gives secondary amide always. Mechanism I have given you, I hope, in aldehyde and ketone chapter. Okay. Now there are very few common reactions we have. The main major reactions we have already done. Okay. There are few more reactions. There are few more reactions which involves the preparation of amines, and those reactions you write down the next reaction from nitro compounds. From nitro compounds. Write down quickly now. These things you have to again memorize. So write down nitro compounds on reduction gives primary amines. Nitro compounds on reduction gives primary amines. Okay. Reagent used for reduction. There are many reagents. So those reagents you write down. For reduction purpose, we can use various reagents like SnHCl. We can also use ZnHCl. H2 nickel we can use. We can use LiAlH4 in dry ether. We can use that is it. Okay, these are the reagent we can use. If you have any nitro compounds, say RNO2, the nascent hydrogen we get from the reducing agent. Suppose LiAlH4 is the agent we have. So this will combines with this nitro compound and forms RNH2, 1 degree amine, plus H2. Right? So 6 hydrogens, 2 we have here, so 2H2 will get. Okay. RNH2 will get 1 degree amine. This you must remember, 1 degree amine we get from this. Okay. Next one you write down from nitriles. From nitriles. Okay. The reagent we use here H2 in Renny nickel. We can use Na in C2H5OH ethanol. That is Renny nickel we call it as. It is just fine nickels we use. The size is very small over here. Nickel also we can write up. RANEY the spelling here, sorry. Or we can also use LiAlH4. Okay. Again, it is nothing but reduction only. only, right? So when you have any nitriles, that is cyanide only, RCN, a reducing agent will provide nascent hydrogen here, LiAlH4, and that gives R CH2NH2. You remember one thing here, the number of carbon atom in the product and this reactant must be same. Okay, so if you have one series of reactions, suppose we have ROH, when this reaction reacts with SOCl2, we'll get some product here and then it reacts with KCN. Then if you have LiAlH4, can you write down the product in all these? If you have ROH in SOCl2, this gives you alkyl halide, RCl, correct? RCl with KCN. KCl goes out and forms nitriles, RCN. RCN react with LiAlH4, it forms RCH2. Okay, this is the reaction we get. Next, write down by reduction of oximes. Reduction of oximes. You have another class now? Maths, no? Okay. Reduction of oximes. This actually we use with aldehyde. Aldehyde we know whenever it reacts with NH2OH, it forms what? Oxime RCH double bond NaOH. This is oxime, right? And when this is reduced with LiAlH4, one hydrogen, this H2O goes out and hydrogen attached onto this carbon and nitrogen and we'll get RCH2 NH2. Again 1 degree amines. These are the reactions. We can write down the mechanism also, but that is again not important. So I'm just giving you the product here. See, number of carbon atom is again same in all these products, right? That you must remember. Next reaction you write down, that is Gabriel phthalimide reaction. Gabriel phthalimide reaction. Right now, this only gives 1 degree amine again. All the preparation method we have seen till now, that is for 1 degree amine. Okay, this is also important. Like sometimes they also ask this gives 1 degree amine, 2 degree amine like this. Okay, this also you keep in mind. Now, if you see the phthalic acid is this. We have a ring and C double bond O, OH, C double bond O, OH. This is phthalic acid. When this reacts with NH3, NH3, this 2 hydrogen from this nitrogen takes this OH and OH, forms 2 moles of H2O. And the compound that you get here is this C double bond O, and C double bond O will be as it is, and these 2 carbons are attached with NH. Understood? Okay. Now in this what happens, we use here any base, that is NaOH or anything we can use. Any base, and then we are using any alkyl halide, RCl. Remember, important thing here it is what the alkyl group that you are getting here. With that alkyl group only, you will get the amines. The final product that you get here, that amines you'll get, that NH2 you'll get from this R only. You'll get this R NH2 as the product. So, like if you have to form ethylamine, right? Then you write down here CH3, CH2, Cl. Methylamine, then CH3, Cl. Like that, you can use this alkyl group here, and you'll get the desired product, right? So what happens? This base will take this H plus from here, and H2O goes out. Right, and this gives you R C double bond O, C double bond O, and this is attached with nitrogen with two lone pair on this nitrogen atom. Right, now this lone pair of nitrogen RCl we have that we are using here. This lone pair will attack onto this alkyl group, and this Cl minus comes out as a leaving group. This attack is SN2 type. Right? Cl minus comes out as leaving group. And the product that you get here is this C double bond O, C double bond O, and this is attached with N and R, one lone pair of nitrogen. This we call it as alkyl substituted. I'll write down the name in the last. Okay, first let me write down. Alkyl substituted phthalimide. Right? Now this H2O, the 2 moles of H2O that we have used. So we are using 2H2O. So what happens here, you see, the product that we have here is this C double bond O, C double bond O, N R. Now in this you have H2O molecule. This H2O molecule, this lone pair attack onto this carbon, right? And another H2O molecule with this lone pair attack onto this carbon, right? And these two bond gets break, right? And what happens finally here, since this oxygen loses its lone pair, so oxygen will have positive charge on it. Here also oxygen will have the positive charge. So one of this hydrogen atom comes out as H plus, and here also one hydrogen comes out as H plus, and both H plus joins onto this nitrogen. Okay, so finally we'll get R NH2 plus phthalic acid will get in the end as it is. C double bond O OH, C double bond O OH. This is the amine we have, which is 1 degree amine. This we call it as Gabriel phthalimide synthesis or reaction. Okay, both are actually same thing. So this reaction is also useful for the preparation of 1 degree amines. Yes. What? Hmm, hmm. See, it's Schmidt reaction generally we use for monocarboxylic acid. Generally. Okay. This is dicarboxylic acid. Two COOH group are there. That also maybe takes place, but we never know. because I have never seen this reaction. Maybe here also we'll get RNS2 and NH2 like this. But again, we are not sure. These are the experimental thing. We do it on the lab, in the lab, so we cannot say. Generally, Schmidt reaction we do when we have monocarboxylic acid. One COH group must be present. Fine. This compound we call it as alkyl substituted phthalimide. Alkyl substituted phthalimide. LIMIDE. Okay. You must remember this R group that you are using here, that only forms the amine. So that you can use accordingly, like whatever it is required according to that, you can use this. Okay. One note you write down into this. One note you write down. Aniline cannot be prepared by this method. Aniline cannot be prepared by this method since aryl halide since aryl halide does not go under nucleophilic substitution reaction. Aryl halide does not go under nucleophilic substitution reaction. Done. Now, the another probably the last method of preparation we have. Okay. So write down by direct ammoniation. By direct ammoniation. In this, it is simple. Write down alkyl halide. In this reaction, alkyl halide reacts with ammonia. Reacts with ammonia, and we'll get mixture of amines. Mixture of amines and quaternary ammonium salt. Mixture of amines and quaternary ammonium salt. Okay. So you see, suppose we have RCl, alkyl halide, and when this reacts with NH3, so what happens? This hydrogen, one of this hydrogen and this Cl combines and comes out as HCl and forms RNH2. This is 1 degree amine. In this method, we'll get mixture of amines. Again, you substitute here RCl. Again, HCl comes out and we'll get R2NH, which is 2 degree amine. Next, RCl and you'll get R3N, 3 degree amine. Now, when you put again RCl here, you'll get R4N plus and Cl minus. This is quaternary ammonium salt. Quaternary ammonium salt. Okay. The direct ammoniation gives you mixture of amines. That's why it is not that useful. Suppose you required 1 degree amine, but if you use this method to prepare 1 degree amine, you will not get only 1 degree. You will get 2 degree, 3 degree, and salt also, right? So all these reactions which gives you mixture of amines, those reactions are not that useful. Okay, because you'll get mixture of amine. Again, what you have to do, you have to separate this amine, 1 degree amine from this 2 degree and then 3 degree, right? So that will also again require much more cost. right? So this is not cost effective method. Generally, we don't use this method to prepare amines, right? So another method we have that gives you mixture of amines is ammonolysis of alcohol. Ammonolysis of alcohol. Write down into this. Alcohol on reaction with ammonia in presence of reagent like Al2O3, alumina, or thodia, THO2. In presence of reagent like Al2O3 or thodia gives mixture of amines. Gives mixture of amines. The reaction is C2H5OH plus C2H5OH plus NH3 with Al2O3. This OH and H comes out as H2O and you'll get C2H5NH2, 1 degree amine. Again, you put here C2H5OH. Then you get C2H5 whole twice NH, 2 degree amines. One more time, the same reaction proceeds. It forms C2H5 whole thrice and so 1 degree, 2 degree, and 3 degree amines we get. Okay. Next, write down properties of amines. We have almost done with this chapter. Okay, there are some chemical reactions of this amines we have, but those reactions are based on the same mechanism that we have discussed today only. Okay, so that you can understand easily. Okay, so we'll do it next class. Okay, just 2 3 properties you write down, then we'll start this in next class, the reactions of this, and that will finish probably in the next class. So we will do this amines chapter into the separate classes. Okay, this is the extra class. Regular classes will do whatever we are doing over there. Okay, so what we are left with, any other thing that is left? uh, so D and F block, I'll just give you the important thing. Okay, there is not much to teach, right? You have to memorize those things. Fine. Okay, and then what is left? Metallurgy is also there, no? I'll tell you. Metallurgy also I'll tell you because those are the complete memory based chapter we have. Okay, so most of the thing we have finished. Anyways, write down the properties of amines. Write down the first point. Lower amines are gases. Lower amines are gases or low boiling point liquid. Right? Lower amines are gases or low boiling point liquid. Next point. Boiling point is directly proportional to the molar mass. Soluble in water. Soluble in water due to H bonding. Okay. Solubility is inversely proportional to molar mass. Okay. These are the few reactions, few properties we have. Okay. So next class we'll start with the chemical reactions of amines. Okay. Okay. Chalo. Bye bye. Take care. Thank you.